Hello, everyone. We will get started in just a second or so once everyone is let into the Zoom. Okay. Well, let me welcome you all. This is Christy Sullivan. I'm the Secretary of the American Society for Cellular and Computational Toxicology. And this webinar is part of our mostly monthly series put forward by the ASCCT and the European Society for Toxicology in Vitro. I want to encourage you to visit the websites of both of our organizations to take a look, learn a little bit about what we do, our activities and programs, and encourage you to join the mailing lists and become a member to support activities like this. The webinar is recorded, and the recording will be posted on the ASCCT website a few days from now in the webinar archive. And you will be able to ask questions of the presenters using the Q&A feature in the toolbar at the bottom of your screen. Please do not put your questions in the chat. Please put them in the Q&A because we can't keep track of them in the chat. There will be a Q&A opportunity after each presenter is finished. So while the presenters are talking, if you have a question that comes to mind, go ahead and put it in the Q&A and we can address it. We also have closed captions enabled. You can turn them on or off if that helps you. And please say hello in the chat and let us know where you're joining from. Just a couple of quick announcements. The ESTIV Congress will be in summer of 2026 in Maastricht. And so I encourage you to visit their website to stay up to date on opportunities to participate. And the ASCCT meeting will be October 21st through the 23rd of this year at the Institute for In Vitro Sciences in Gaithersburg, Maryland, just outside of Washington, D.C. We have, for one more day, session and continuing education course proposals are open. So please consider submitting a proposal, and we will open up regular abstract submission and poster abstract submission a little bit later in May through the early summer. As you know, you can visit our website to find out the calendar of events. We have a number of ASCCT-ESTIV webinars coming up. You can see on the screen for May and June. And then there's also some announcements for partner webinars and activities. If you are an ASCCT partner or sponsor, you're welcome to let us know about activities like this, and we'll put them on the calendar. So for today, we have 3 speakers. All 3 of our speakers have won awards at the most recent ASCCT annual meeting. So congratulations to all 3 of you. First to speak will be Gabriela Correa. She is a researcher in the field of human and environmental toxicology with a particular focus on in silico methods. One of her life goals is to contribute to research aimed at replacing the use of animals in chemical safety testing. In recent years, she's concentrated on this mission and has actively shared her knowledge at various scientific events, making it accessible to all interested parties. Our second speaker will be Amber Daniel, who is a senior toxicologist with the Predictive Toxicology and Information Sciences group at Inactive. She holds a Bachelor of Science in Animal Science and a Master of Toxicology degree, both from North Carolina State University. As a contractor supporting the National Toxicology Program Interagency Center for the Evaluation of Alternative Toxicological Methods, or NICETM, she's worked on a variety of projects to promote the development, use, and regulatory acceptance of alternatives to animal use for chemical safety testing, including validation studies of in vitro test methods and defined approaches to detect potential chemical safety hazards. And then finally, we will hear from Dr. Sezin Aday. She is a research associate at the University of Pennsylvania and a program manager in the BARDA-funded Inhalation Toxicology of Chlorine Gas on a Chip project. She develops organ-on-a-chip models to reproduce living tissues in their native microenvironments to understand cell-cell interactions and to find biomarkers for different injuries. All right, well, with that, I will go ahead and turn it over to Gabriela. So I will let you share your screen and start your presentation.
Hello, everyone. My name is Gabriela. I'm a product safety researcher at Grupo Boticário, and today I will present my work assessing computational approaches for predicting estrogen binding, for predicting estrogen receptor binding. Here is a quick overview about Grupo Boticário and our branches. Grupo Boticário is a large Brazilian cosmetic company that exports to many countries. You can check more about the company in this QR code. And now, to start, I would like to provide some background about the context of my work. As you can see, my work is about endocrine disrupting chemicals that are natural or synthetic substances that may mimic, block, or interfere with the body's hormonal system. And these chemicals are associated with a wide array of health issues. Some well-known targets for EDCs include nuclear receptors such as estrogen, androgen, and thyroid receptors. There are many publications about endocrine disrupting chemicals in cosmetic products, which has raised concerns. And this study aimed to assess the sensitivity and specificity of in silico tools in predicting the binding of chemicals to estrogen receptor. And this is an important endpoint for cosmetic products, considered human health and the environment. Now let's move on to the methodology. For the training set, we select 20 proficiency chemical substances from OECD 455 and 493, which are in vitro assays used for evaluating chemicals binding to estrogen receptor. In table 1, you can see all the 20 substances. And for the training set, we selected 14 positive substances that exhibit affinity for the receptor and 6 negative substances that don't exhibit affinity for the receptor. In figure 4, you can see the study design. So the training set was composed by the 20 proficiency chemical substances from OECD 455 and 493, as I said. And for the in silico predictions, we used 4 in silico platforms: Endocrine Disruptome, Vega, Danish, and AutoDock. And based on the results of the predictions, we evaluated the coverage, out of domain or no predictions made, corrective predictions, and we also evaluated sensitivity, that is truly positive active substances, and specificity, that is truly negative inactive substances. Here are the models used for endocrine disruptome, Vega, and Danish. And AutoDock was used to perform molecular docking. Here you can see the protein structure used. And for the results, substances were considered positive, indicating a high probability of binding when the binding affinity was equal to or greater than -7.5, and substances that obtain values less than -7.5 were classified as negative. Now let's look at the results. In table 2, we have the in silico prediction results for all the substances evaluated. In this column, we have the OECD results from proficiency substances. And in another, we have the predictions, the results from predictions. For Vega and Danish had similar results, as you can see. Vega correctly predicts all positive substances and one negative substance out of domain. Danish had 2 out of domain predictions, one for a positive substance and one for a negative. Both tools, Vega and Danish, are QSAR tools. And for Endocrine Disruptome and AutoDock, these tools are molecular docking tools. And as I said, for Danish and Vega, we also had similar results for the molecular docking. Endocrine Disruptome had 5 positive substances predicted as negative, and AutoDock had 3 positive substances predicted as negative. And it's bad when a silico tool predicts a positive substance as a negative, because it leads to a false negative. And here we are missing the real risk. A false negative means the tool fails to identify a substance that does have the potential to bind a receptor. And for endocrine disruptome and AutoDock, we also have one negative substance predicted as positive and one out of domain for endocrine disruptome. In table 3, we have the agreement percentages between OECD proficiency substances and the in silico predictions. For coverage, we had similar results for all the tools. For Vega and endocrine disruptome, 95, for Danish, 90, and AutoDock was the only tool that predicts results for all substances with 100 in coverage. Vega and Danish QSAR achieved 100% in sensitivity and specificity. These tools correctly predict all positive substances and all negatives. Endocrine disruptome showed a low sensitivity due to false negatives, as I said in table 2. And AutoDock showed promising results, but when compared to QSAR tools, we had 3 false negatives as endocrine disruptome. We also calculated the balance accuracy. Balance accuracy is the average of sensitivity and specificity, indicating a model's performance across both positive and negative substances, positive and negative predictions. For Vega and Danish QSAR, we achieved 100%. For endocrine disruptome, we achieved 72%, and AutoDock, 80%. In conclusion, in silico approaches are fast and cost-effective alternatives to animal testings. The results demonstrated the potential of in silico tools in predicting the estrogen binding. QSAR tools performed well when compared to molecular docking in predicting estrogen receptor binding. These results can complement in vitro and literature data, and they offer valuable pre-screening for new substances with endocrine disrupting potential. We have several opportunities for future research. We want to evaluate a new training set to screen a large number of substances using databases like FDA, Endocrine Disruptor Knowledge Base, Endocrine Disruptor Lists, and Endocrine Disruptor Assessment List from European Chemicals Agency. We also want to evaluate another receptors like androgen and thyroid. Due to the complexity of the endocrine system, it's important to evaluate different receptors, pathways. And based on the new training set, identify a combination of methodologies or softwares to maximize performance in screening new substances. In this work, we have better results. We had better results for QSAR tools, but with a new training set, maybe the results can be different. And it's very important, try to select substances commonly used in cosmetic products for the new training set to assess the performance of the models within this specific chemical space. Here are the references used. Thank you for listening. I would like to thank ASCCT for the opportunity to present my work and to attend the reunion last year. I would like to thank the co-authors of this work, Andressa, Desiree, Tuxtenio, and my colleague Anax for his valuable contributions. Here are my contacts. This is our team, the Safety Assessment Management. And I would like to see you all this year in Rio de Janeiro for WC30.
Great. Thank you very much, Gabriela, for sharing this, this work with us. We have a couple of questions for you in the Q&A. And to an extent, they've been answered a little bit, but I'll ask for your additional comments. So there's some questions around the initial test set that you used. Were those compounds within the models training set? Do you know the extent to which were some of them or all of them part of the models training set?
We use free softwares, and it's difficult to evaluate it when a substance is inside the training set. So for these substances, I didn't evaluate these but for the new training set, it's important to consider this.
And then, as you say, you're going to build a larger test set with chemicals that are outside the training set, chemicals that are more specific to your company's sector.
Yes, as I said, it's important to select substances commonly used in cosmetic products to understand the results with these specific substances.
Yeah. There's actually a question that is reflecting a question I had about the docking models, which are usually more reliable than QSAR for predicting receptor binding. And I'm just wondering if you have any ideas about why those models didn't perform as well.
It's a question that this is a question that I made. Anax helped me with this work, and he is especially in silico methods, but we didn't understand very well how in this work molecular docking didn't perform very well. But for the new training set, we want to evaluate this too, because we had similar results for endocrine disruptome and AutoDock, and it's a very interesting question how this happened. But
Yeah.
now I don't know, but I will evaluate this.
Good. That sounds like a good follow-up exercise. Okay, well, thank you again so much. Thank you all for your questions. And now we will turn it over to Amber for the next presentation.
Hi, everyone. Just share my screen really quickly. Great. So thank you so much to ASCCT and the organizers for the kind invitation to come and share some work that I've done, that I've led under the NICEDM contract to develop defined approaches for predicting eye irritation classification of agrochemical formulations according to the GHS and EPA classification systems. So here's a super simple outline of what I'll be covering. I don't have any conflicts of interest that I need to declare, so I'll jump right into some background information. The DRAISE rabbit eye irritation test was developed a little over 80 years ago now, and was later endorsed by some regulatory authorities as a standard method for product safety evaluations. As development of non-animal methods started to catch on, those new approaches have typically been assessed by directly comparing their performance to that of the rabbit test. However, based on some increasingly documented limitations of the rabbit test, more recently, there's been a movement toward instead evaluating alternatives based on their reliability and their relevance to humans, which is what we did for this study. There are multiple in vitro, in chemico, and ex vivo assays that at this point have been developed and evaluated for their usefulness in predicting the eye irritation endpoint. Some of them have been adopted as test guidelines under the Organization for Economic Cooperation and Development, or OECD, which indicates that they're internationally accepted as standard methods for chemical safety testing. Defined approaches, or DAs, as you'll probably hear me call them in this presentation, these are rule-based data interpretation procedures that are applied to data from one or more specified methods to derive a prediction. So there are, in fact, some defined approaches for eye irritation and corrosion that are described in OECD Test Guideline 467. However, the DAs in that test guideline were, first of all, they were developed for the GHS classification system only, which is somewhat different from the classification system that is used by the US EPA Office of Pesticide Programs. And additionally, the applicability of the defined approaches that are described in that test guideline are limited to, it's mostly non-surfactant neat liquids. So agrochemicals are typically very complex mixtures that commonly contain surfactants as ingredients. And therefore, there's still a need for defined approaches that are applicable to agrochemical formulations. So to address this, NICEDM, in a collaboration with the PETA Science Consortium International and EPA Office of Pesticide Programs, set out to test the eye irritation potential of various agrochemical formulations using a common set of non-animal methods, and then using the data that were generated in addition to historical rabbit data, use those data to develop DAs for predicting GHS and EPA classifications. So the test substances were all donated by CropLife America agrochemical companies. There were specific criteria for selecting the chemicals, including, importantly, that they had available historical rabbit data or ocular irritation classification information. They were selected to represent the 3 most common agrochemical formulation types and to represent a good distribution of the full range of GHS and EPA hazard classifications. So testing was conducted in a 3-phase sort of approach where we test a few formulations in a few methods. Phase 2 sort of refine those methods, add some more formulations so we have the full categories covered. And then in phase 3, tested even more formulations and added additional methods as they were developed or validated since the beginning of testing. So at the conclusion of phase 3, we had 29 formulations that had been tested across 5 methods. There is a NICETM report where you can read more about all of the methods and protocols that we tested. But for today, I'm just going to focus on the 4 that were selected to move forward for inclusion in DAs. So in addition to our evaluation of the test results, which indicated that all of these methods were applicable to agrochemical formulations, we also selected these based on their status as an OECD test guideline and on their relevance to humans. So BCOP, epiocular, and time to toxicity for liquids, these are all OECD test guideline assays. IRS, that is not currently described under any test guideline, but it does include several traits that indicate it's more human relevant than compared with the rabbit eye test, such as precise control of the dosing application and termination, quantitative results, and additionally, the Cotres et al. Peer-reviewed evaluation suggests that it may be suitable to include in defined approaches for liquids. Additionally, BCOP is obviously bovine-based, but epiocular, time to toxicity for liquids, and IRS are all considered human relevant based on their use of human tissue models. So this is a picture of 2 defined approaches that I'm not specifically discussing today, but I would be remiss if I didn't mention them because they're sort of the first product of this testing. And they're described in a paper that was led by Anna van der Zalm from PETA Science Consortium. 2 defined approaches that are tailored specifically to the EPA classification system, consisting of either BCOP with histopathology alone or combined with epiocular. And we've since built upon these to create 4 DAs that I'll be talking about today for both GHS and EPA classification systems. So how did we, make them applicable to both classification systems that are different? So because not all of the standalone methods that are included in the DAs they don't all include EPA classification criteria in their respective prediction models. But however, given the similarity of the 2 classification systems, we considered EPA category 1, 2, 3, and 4 pretty much equal to GHS 1, 2A, 2B, and not classified respectively in the development of the DAs. So one notable difference is in the labeling requirements for protective eyewear. So GHS requires that hazard labeling be included for substances that are GHS category 1, 2A, and 2B, but there's more flexibility for the manufacturer to specify appropriate PPE. And conversely, the EPA specifically requires PPE labeling as a component for EPA category 1 and 2 substances, but typically not required for EPA category 3 and 4. So the labeling for those mild irritants is a little bit different under the 2 classification systems, and I'll discuss that a little bit more when I get to the analyses. So these are the first 2 DAs. They're very similar to the ones that are described in the van der Zalm paper, but refined to add a little bit more protection of human health and also to demonstrate applicability to both classification systems. And then we added these 2 new defined approaches that involve additional in vitro assays, time to toxicity for liquids with BCOP and IRS with BCOP. So I just wanted to break down just a little bit using the BCOP plus defined approach just to kind of explain a little bit more better understanding of how the flow goes. So according to the BCOP test guideline, in vitro irritation score greater than 55 is sufficient to classify corrosive. We included that into these defined approaches, but also included an option to continue on even after that in vitro irritation score to potentially downgrade to GHS category 2A or EPA 2. What's a little bit different is if there's an in vitro irritation score that's less than 3, we included histopathology because we had several formulations where histopathology led to a more severe classification. And a little bit about the histopathology model. It's conducted based on the depth of injury and using a model of the more severe, if histopathology is more severe, it would lead to a more severe classification. So given the limitations and the low reliability of the vivo test, we did not assess performance of the DAs based entirely on concordance with the in vivo data, but instead, to overcome the limitations of any one approach, we conducted orthogonal concordance analyses. So for each formulation, we use the in vitro testing data to apply the 4 defined approaches, and then orthogonally compared the classifications predicted by each of the DAs and the historical rabbit data against each other. So concordance was evaluated based on agreement of the 5 approaches. Predictions were orthogonally concordant when they aligned with at least 2 other approaches, or if a majority, at least 3 of 5 approaches achieve the same prediction, and considered orthogonally discordant if they misaligned with the majority prediction. And going back to what I was previously discussing, the differences between GHS and EPA, we also evaluated whether orthogonal discordance affected the hazard labeling of GHS or PPE labeling according to EPA. So here's the color-coded results for the GHS classification system. We were able to determine a majority prediction, which is listed in the right-hand column, for 97% of the formulations. The only one where we did not have a majority of approaches agree on one majority prediction, notably, is the one formulation that we had insufficient quantity to test it in all of the individual in vitro methods. So orthogonal concordance with the majority prediction ranged between 82% and 93% for the defined approaches, compared with only 71% concordance for the historical in vivo data. What I really want to draw your attention to, the color coding shows differences in whether the prediction would cause a change to whether or not there's hazard labeling included. So importantly, if you see the red, that's where orthogonal discordance with the majority prediction would result in hazard labeling being not required when it does seem to be that there's indication of some eye irritation, so therefore would be underprotective. Similarly, here's the EPA results. Again, we were able to achieve a majority prediction for 97% of the formulations. Orthogonal concordance was 75% to 93% for the defined approaches, compared with 79% for the historical in vivo data. So you'll see that the only one where there were any formulations that were underprotective for PPE labeling relative to the majority prediction is the one formulation based on the historical in vivo data. So here's just kind of an overall view of all 4 of the defined approaches together. Basically, we concluded that the defined approaches are equally or more protective of human health compared with the in vivo test, and that the defined approaches present an opportunity to fully replace the in vivo test for determining GHS and EPA hazard classification and labeling for agrochemical formulations. So I would like to acknowledge the picture there is the NICEDM group and contract support staff. In the picture there, I would really like to thank all of the contributors, the collaborators, the agrochemical companies that donated, the testing labs that conducted all of the testing of the individual methods, and especially all the co-authors for their valuable contributions. I'm really happy to say we heard yesterday that a manuscript describing this project was accepted for publication. So anyone that's interested should be able to read all about it very soon. And I'm happy to take any questions.
Great, thank you, Amber. I gotta say, it's I really appreciate the presentation. It's a really great example of how we can practically decrease reliance on the sort of in vivo, in vitro concordance, because we talk a lot about trying to do that, and it's a really nice quantitative demonstration that you've provided.
Thank you.
There is one question, but oh, actually, this is a question for Gabriela. Gabriela, if you wouldn't mind jumping in to type an answer for that one. I have a question for you, Amber, which is, we have talked a little bit about this in the context of skin sensitization, where we have a number of different options for defined approaches, even for the same same use case or same outcome. And I'm wondering, there's 4 options. They have basically relatively similar performance with slight differences. And so I'm wondering if there's been any discussion about how you work toward some consistency with pesticide formulations in terms of either trying to figure out how you would choose based on your formulation that you're testing and its chemical characteristics maybe, or phys-chem properties, which one would be the best option, or if there are other kind of signals that you have gotten from the agency about, like, if there's certain preferences, or from companies, if there's many discussions like that for one over the other.
Yeah, no, that's a great question, and I get asked that a lot, actually. So we like to say this choosing which one should be considered on a case-by-case basis. So it's going to be usually agrochemical companies that are, selecting a defined approach that they should use. For the testing, we were not provided a lot of physical chemical information because that's all proprietary, but those companies would likely have access to that. So we like to say consider the physicochemical properties of the formulation in choosing which one would be best. So for example, let's say you're expecting it to be non-irritating, which, I mean, most agrochemical formulations are. Typically, probably the DAEO plus is going to be the quickest and most efficient in that case, considering that there is such high specificity of the epiocular assay. If you're expecting it to be irritating, DA-IRS plus might give you the most insight on reversibility of corneal injury. That IRIS assay measures expressions of genes that are involved in the wound healing process. And then there might be other practical or logistical considerations, like if you have access to all of the tissues or reagents that are needed to conduct one of the defined approaches.
Okay, great. Yeah, that's a lot of interesting considerations. So thank you very much.
Yeah, thank you.
So there is a question. I think what they're wondering is there other data besides test data used within the defined approaches, like phys-chem properties or other information about the formulations?
No, it's not involved within the defined approaches. It would just be considered ahead of time in selecting which one.
Okay, that makes sense. Thank you. Okay, well, thanks again for your presentation.